Okay, so we're going to be starting a new section where we talk about rational expressions. So what we're going to be doing, right, is looking at something which is a fraction. That's what a rational is. So it looks like this, where f and g are both polynomials. If you want, it looks like an x to the n plus an minus 1 x to the n minus 1 plus a2x squared plus a1x plus a0 divided by bn x to the n plus bn minus 1 x to the n minus 1 b2x squared plus b1x plus b0. Now, I don't need you to necessarily memorize this, but what you do have to know is that these represent the polynomials, which is the exponents of the variables are all positive integers or whole numbers, and the an's and the bn's, or the numbers in front of the variables, are just constants. Any real number like 2, 3, pi, a half, 23 over 2. Okay? So they're always polynomials divided by polynomials. Okay? Now remember, we have a fraction. So what is the restriction of a fraction? We can't have the bottom divided by 0. So that is going to be the domain of the rational functions. So domain of rationals no division by 0. So if you want to check this, what do? You set the bottom equal to 0 and take that point out of the domain. Okay. Now we've done this before when we were just talking about domains in general, but what we are going to do now is we're going to split the division by 0 into two different parts. So the first part is called the vertical asymptote. And the second one is going to be called whole or removable discontinuity. Now, a vertical asymptote happens when you have division by 0 and there's no simplification that can get rid of it. The B, or the whole, or the removable discontinuity, happens when you simplify it and it disappears. So it is removed by simplification. So let's look at these two examples and we'll see which one is which. Okay, so this first example, right, there's no simplification that can happen. So here, the domain we solve by setting the denominator equal to 0. So 2x is equal to -1, or x is -1/2. Okay. This is the restriction, so it cannot be -1/2. So what that tells us is the domain is everything except -1/2. Okay. It does not include this. In this one, though, notice that these cancel, right? And all that's left with is x. Well, if I try to find the domain here, there's no division by 0, there's no square roots of negatives. So the domain is going to be -infinity to infinity. But that doesn't work because we're not trying to find the domain of this. We're trying to find the domain of the original, which still cannot have the denominator equal to 0. So this also has the -1/2, except the difference is going to be, this one was not removed, so this is a vertical asymptote. At x equals -1/2. This one, though, is a removable discontinuity, or a whole, at -1/2 x equals. Now I'm going to draw both of these so you can see the difference. A vertical asymptote means that the graph approaches the vertical asymptote but never touches it. And what it's going to do is it's either going to shoot up and down or both in the same direction. You'll learn how to graph this in a different class, so I'm just going to show you what it looks like. The vertical asymptote is there at that negative a half, right? That's what we said. X equals is a vertical line. And it does this. So you see how it approaches the vertical asymptote but never touches it. It can never touch it because it's not in the domain. I cannot plug this in and get a function output, which means there's no dot, right? I cannot plug it in. This one, though, notice that it simplifies to just y equals x. Well, that's a line. Looks like this. Except this one right here, this x equals negative 1/2, cannot exist. So you get a hole, right? So notice that the function is the y equals x function without negative 1/2 in its domain. So y equals x without this negative 1/2 in the domain. So there's a hole.